Good morning, and thank you again for joining us at .local MongoDB here at the Highline stage. My name is Drake Haywood, and I'm part of the go-to-market enablement team. We have the distinct privilege and pleasure of introducing Prakul Agarwal. Prakul comes to us from our solution architect team as a product management lead for machine learning, and today Prakul is going to be walking us through the MongoDB Generative AI application stack. We'll be holding time for a question and answer segment following the conclusion of Prakul's session. So if you do have any questions, be sure to raise your hand at that point, and we will come speak to you. But other than that, Prakul, thank you for leading our conversation today.
Thank you so much. And is this mic working? Can I get a thumbs up? All right. Welcome, everyone. I'm Prakul Agarwal. I'm a senior product manager here for machine learning and AI. And we wanted to talk about how do you put together a generative AI application together faster with MongoDB application stack. So we have been in a rapid growth stage. Just last year, we presented about emergence of this whole generative AI. ChatGPT had come out, became popular. We were transitioning over from the traditional MLOps space. And things have changed a lot, where we have something of a generative AI stack, and happy to dig into that. But just to get started, so the agenda for today is really I want to talk about the state of the AI applications that we are seeing across our customer base. Secondly, I want to dig into the specific architecture pattern called RAG, and what are the challenges there. And then I want to introduce the MongoDB Generative AI application stack and how that helps you put together these applications like RAG faster, better, and in a safer manner. And of those components, we go into primarily 5 components that constitute that AI stack. So with that, let's dig in. So from a current perspective, one of the biggest use cases that we see is this semantic text search. As you all know, with this new class of models, you can take your text data, convert that into these things called vector embeddings using an AI model. That gives you the ability to search across semantically, that is based on the meaning of things rather than the keywords that are actually present there. That opens up some exciting possibilities. So in this example query, we search for a very natural conversational syntax, like give me some movies which have imaginary characters, maybe from outer space, who are at war with each other. And that pops up a bunch of these results, which do not necessarily contain these keywords that would constitute it. Extending the power of this paradigm, you can be doing the similar thing on image search data sets. So in this example, we search for houses with swimming pool. But what is important is that these keywords, this tagging does not exist in our data set. We really are going off these actual images, and we're using these machine learning models to be able to understand images, convert that into a way where it can be queried effortlessly. Extending that is this big use case of Q&A. So this ranges from having financial analyst kind of use cases to having customer service use cases, where you have natural language conversation with your data set, right? And everyone has used tools like ChatGPT, Claude, where you can ask questions to these large language models, right? So with RAG, we power these QA where you can marry your private data sources with public information using the reasoning capabilities of this emerging class of AI models called large language models. On the left bottom, you can see asking a question like, how much better is GPT-4 in reducing hallucinations over GPT 3.5 to ChatGPT, where you essentially get an answer where it says, I do not know. I have not been trained on that kind of a set. On the right, we will show you how you can get to a Q&A answered specifically using a private knowledge source. The other big use case that we see across our customer base is these conversational agents, where going beyond the step of just Q&A, you can marry together various knowledge sources, information that you have about the customer, their activity, their interaction, to be able to power these use cases like a customer service chatbot. In this case, can I return a product that I purchased last week? That's a question that the user asks the chatbot. And now the AI agent is supposed to disambiguate a bunch of things here on what customer it is, what product did they buy from last year using their product catalog, and then being able to figure out what the return policy is for that specific category of product. So with those broad use cases, I think all of you are probably aware of RAG, and that is one of the most critical patterns of putting together these powerful applications. So just as a primer, so typical workflow for a generative AI query comes from user asking a question to the large language model, getting back a response. So with RAG, and you have a bunch of these large language models. You have from OpenAI, you have Cohere, you have a bunch of open source models available on these repositories like Hugging Face. With RAG, the way this paradigm changes is we intercept the user's query, pass it to a vector database that is able to provide the context, and now pass along that query along with this additional context from our private knowledge sources back to the LLM. So what does this look like from a more architectural standpoint? So RAG, Retrieval Augmented Generation, is this process of combining retrieval, which is pulling information from your retrieval system, mostly using search methodologies like vector search, BM25 search, hybrid search. We'll get into that. And then putting that into a generative model to put together the output. It's a two-stage process where across on the top right, you can see is the indexing path. You have your private knowledge sources. The power of this paradigm is it extends to your structured sources, things like your tabular data, your MQL data, as well as your unstructured sources. So could be your PDFs, could be your image files, audio files, Google Docs, Slack, bunch of knowledge sources. So we take that knowledge source, put that into an indexing pipeline, and that is stored into our retrieval system. So once this process is done, you're ready for user queries, where on the bottom left, you can see user asks a question that gets passed on to a pre-retrieval process, which gets onto a retrieval system. And based on the retrieve results, you put that into a post-retrieval process, pass it on to your large language model along with a prompt. And that's how you get to a point where you get a specific, well-informed answer. Now, just as a motivating example, right, of what that kind of an unstructured knowledge source could be, we want to talk about this one PDF, which is a 10K document for a stock company, which is submitted every quarter to the US Commission for Economics and stuff. So this is a PDF, just an example. It consists of 160 pages. And this is the knowledge source that we want to be building our Q&A RAG on. So what you would find is data cleanup. This kind of a document is complex, has a bunch of tabular data, tables which are in line with other texts which are independent, but also a lot of complex text paragraphs where there is some kind of relationship between how the information is overlaid. So how do we put together this thing, right? So now, essentially, for a query, the objective is to ask a question like, what is the year-end FY 2018 net PP&E for 3M? Answer in US $1 billion. So this is a pretty loaded query where what exactly is the meaning of PP&E? That's a very specific word that is contextual specific to this data set. It is restricting to a particular financial year. It is talking about reasoning capabilities. Don't just give me an answer. Give me in US $1 billion. And the answer that we want to be getting is 8.70. And we want to be able to point it to a particular answer source on how exactly, where was it retrieved from. So in this case, it existed on page number 58. And it was part of a tabular data that it needed to parse through. So that's a pretty complex process. I'm sure a lot of you are practitioners here and have been dealing with the issues that come up in such kind of a process. But now, talk about those issues, right? What are those issues that we see? So from the top right, first thing is, how do I parse these complex data sources? We talked about tables, paragraphs, having all those interrelationships. What do we do with that? You would need to use something like a embedding model as part of your indexing and your query pipeline. So what embedding model to choose? What are the considerations there? Once you have it in your retrieval system, it's a complex question to answer. What retrieval parameters should I have? Right? Like for retrieval parameters, we'll dig a little bit into that. And then as you're passing stuff into your LLM, how do you choose your LLM? What does it mean? A lot of the practitioners would know the cost implications of these models, the kind of privacy considerations, the kind of hallucination impacts, etc. And once you have generated an output, how do I actually verify that the response that has been generated is something that's trustworthy, that is something high quality, that has actually answered the query that the user put together? So what are the ways of evaluating this kind of a system? So with all these challenges is how we think from a product perspective on putting together the stack for you. So introducing the MongoDB Generative AI stack. So this stack constitutes broadly of 6 categories that we put together. So from the very bottom, we start off with these AI models. AI models primarily are your foundational models, generative models, and your embedding models. Up the stack is your model hosting or serving platforms. Followed up is the data integration, the data pre-processing layer, followed by the vector database, which powers the memory for all these applications. And to put these together, you get your LLM app orchestration frameworks, followed by your LLM observability and evaluation frameworks. So with MongoDB and a bunch of integrations and partnerships that we have for you, this is what this stack looks like. So starting from the bottom, you talked about foundational models. So there are these amazing models with Anthropic, OpenAI, Mistral AI, Google has a bunch of models, and this is a restricted list. But these are some of the leading model providers. With embedding models, we see some amazing embedding models from Cohere, from Nomic, OpenAI, Mistral. Model hosting platforms are seeing a rapid innovation. There are a lot of considerations that go into it. So there is a big list of companies that we partner with to make your journeys faster, followed by these data pre-processing. We'll talk about what companies like Unstructured and Superlinked are doing and how they're integrated with MongoDB. Vector database, your operational category is MongoDB, obviously. And then for your LLM orchestration, there are some of these popular frameworks that I'm sure a lot of you have been using, but we have native integrations with these. We'll talk about LangChain, Llama Index, Haystack from DeepSet, Microsoft Semantic Kernel, and then followed by the LLM observability and evaluation. So let's dig into each of these components and what are the kind of considerations that we are seeing our customers run into and how they are putting together a stack that works for their use case. So the first category is your foundational models. So with foundational models, there is a large range of options, and these are mostly the popular ones. As you're aware, there is a huge list of open source models that keep coming out. Meta recently launched a Llama 3, which has surpassed performance of all the previous models. Llama 2 has achieved on multiple benchmarks equivalent performance to OpenAI's models. So it's a very fast-moving and rapidly evolving space. But what are the big questions that our customers are asking for, right? One is which LLM to choose. And the second is how do I obtain the right performance cost trade-off that is inherent there. So to dive into that, let's go back to the example which we started off with, that we want to put together a Q&A powered by RAG on this data set from 3M on what is the year-end FY 2018 at PPNE. And typically, with the RAG pipeline, we would combine this with a prompt that you see as part of your LLM query, We want to ground this, so we provide a prompt that first thing is the role. Assume that you are a public equities analyst. This is the prompt you're providing the LLM. And we want to ground it, so we are instructing it to answer the question primarily by using information that's shown in the balance sheet, so that it is not going off the rack and you can be sure it is grounded in truth. So we run a bunch of experiments, right, across a bunch of models. So two most popular model categories, Mistral and OpenAI. So for this question, the answer is supposed to be 8.70. Now, you would see the actual outputs that you would see from these different models as you go through it. So we compare across Mistral Large, which is a closed source model from Mistral, followed by Mistral Small, which is the mixture of experts, 8x7b model. Mistral Tiny is their 7-bill parameter model. And GPT 3.5 and GPT 4 are these popular models from OpenAI that you're already aware of. So for this setup, we had a retrieval parameter with k equal to 14. And we got to the right answer with all these LLMs. What you would see is how certain LLMs are not able to reason properly. So if I can point you to the Mistral Tiny, the one in the middle, you would see this thing that is marked in red on the very bottom. So instruction was very specifically that to answer this in US billion dollars. But what we are getting here is the right answer, which is 8.7. And it is approximating it to 8.78, but answering it in million, which is like a false piece of information. So that's a kind of like evaluation that you would want to do, right? And the question is why not just choose the biggest, the most accurate model? So the answer to that basically lies in the fact of these models' cost, depending on what it takes to run them, right? So for all the previous classes of model that we talked about, you can see the cost in the table below, which is basically the cost. It is cost like 1 million output tokens in US dollars. So for the largest model from Mistral, it cost $24 per million tokens, followed by Mistral Small, which is 1.97. This is a crazy difference in price point, followed by Mistral Tiny, which is 0.46, right? Within OpenAI's model, you can see 3.5 to 4. It's almost 15x price difference, like $2 versus $30. So now in this case, we really got to a point where all the LLMs are able to answer, right? So the obvious answer is maybe I'll just go with the cheapest model, right? That can provide me the right answer in this case. But let me talk about a failure scenario. So the failure scenario is the same question, but the retrieval parameter has been changed to 13. So this is where, from my retrieval system, I put together the top 13 chunks of information that corresponded to the user query. In this case, it's basically we are not providing enough context to the LLM. It does not contain the chunk of information from that PDF which contained that answer. So in this case, the expected answer is actually for the response to be that I do not have enough information. I can't answer this question. And what you see in the table below is all the ones marked in red, all these different models actually went on, gave an answer, and did not say that I do not know. Only two models, one Mistral Large and GPT 4, were able to reason correctly that based on the instruction and the knowledge provided, the answer does not exist, and went on to say it's not something that it could be answered. So on a similar grading, right, like we were able to get to the right answer, right reasoning capabilities on the largest, most expensive models. So that's the kind of evaluation process, right? Like for a lot of these models, like with the rack systems, the typical stack expenditure that we see across the customer bases is spending of 10 to 20% on the embedding models, 10 to 20% on the vector database, with the remaining lion's share of chunk going into these generative models. So a lot of those actually make your business use case of putting together an application unfeasible. It's not economical to actually have this in production, scale it to all the users that you can have. That's where a question of like, what is the use case? Is it an internal kind of a service which is powering your knowledge base versus if you want to have it across user base, right? That comes into picture. So just quick takeaways, right? Like, depends on, there's no correct answer. Depends on your use case, how you want to put together. You have to think of LLMs foundational models in capabilities across the quality, the speed of token generation, and the kind of price point that it comes to you. Figure out the right fit for your use case. We provide a bunch of these tools to put together evaluation across these models for your use case. And very big piece is your data and your retrieval system is your moat. That is the gold of this current world. And MongoDB's application stack approach is we work with a wide range of these LLMs. So you can choose a proprietary for your use case, swap in, swap out as needed. So with that, we go to the embedding models. So embedding models, bunch of providers, big questions, how do I use my embedding model, and how to obtain the right price performance cost trade-off. So with this, let me offer you a case study of how do you go from like building something with OpenAI. We're using the previous version, which is ADA2. They have a bunch of these versions. So this, in the embedding realm, for every 1 million queries with 500 tokens, right, costs $50. It may not seem significant, but these are the kind of volume you would be doing multi-million per day as you scale in production. Going from that OpenAI to a model which is open source called BGE Large takes the cost down from $8 to $3.5 to $1.5, depending on how and where you're using it. Now the big question is, how do I manage the accuracy? So for accuracy, there is a benchmarking for these models called MTEB. So what you can see here is like OpenAI's embedding model is less accurate. The more the score is better on the right. So 61 score on the aggregate MTB versus 64.23. And the implication of choosing between these models is that you're getting a better retrieval performance for almost 6x the lower price. And as you go down with like further optimizations, we talk about self-hosted options, you can drastically reduce your price points. So with that comes the question of model serving platforms. And big question there is Fireworks, Together, Anyscale, Hugging Face, bunch of these hyperscalers. Big questions are, how do I experiment with these models quickly? And how do I ensure data privacy and safety? So things that we talked about building your RAG application, this is the layer where you will iterate on. So first thing, to experiment with models quickly. Platforms like Fireworks, Together AI, and Anyscale provide you a bunch of these open source models that you can use on a multi-tenant architecture. Provide you a bunch of options to improve the speed of the generation, right? Bunch of innovations coming out in this space. The second piece is about how do you ensure data privacy. So if you have an enterprise use case, you really care about things like having guarantees that your data is not used for model training, being able to choose multiple data centers, being able to fine-grain access control on who gets access, to being able to use things like private link. So with a lot of our AWS Bedrock, Vertex AI, Google, Microsoft Azure, these are the kind of enterprise-ready platform that we provide for a use case. So that comes to the question of data pre-processing, data integration. As we talked about multiple data sources, how do I connect to them, and how do I parse complex documents? So this is kind of like how that pipeline would look like. And this is a library called Unstructured that we integrate with. It's a complex process, right? Multiple data sources, you put it into a pipeline. Sometimes basic chunking is not enough. For tabular data, you really want to be using these OCR-like models to extract information. So you want to be able to choose between different stages, right? So there is option that range from taking 10 seconds a page to all the way to 0.4 seconds a page. And you chunk it, put it into MongoDB. So bunch of ways that will help you get there. That brings us to vector database. Hopefully all of you are aware. I've been using it, would love to know what you're doing with it, vector search. But that's a vector database integrated into MongoDB's Atlas platform that we announced in the last .local and have seen massive growth here. So with the retrieval system in your RAG pipeline, it's a iterative process. Start off with a vector search, go to vector search with metadata filtering, go to with post filtering, being able to combine that with text search. This is a traditional keyword-based search, BN25, having ability to combine vector search and your text search with hybrid search. So I will skim through this, but like we have a bunch of sessions around it, but you pre-filtering versus being able to do your vector search before and combining that with metadata filtering, bunch of improvements in your accuracy. With post filtering, it has implications, leads to different results. And then being able to have this thing called hybrid search, right? Launching a query with vector search and atlas search, being able to combine them, gets you to great results in some out-of-domain domains, right? Where your embedding model is not trained on that kind of domains. So we have some more in-depth sessions to go into these concepts today, which brings us to LLM app orchestration frameworks. Now, all these steps are pretty complex, pretty varied, that you saw that we have been juggling around with. So the big question is, how do I quickly get started with building these LLM retrieval systems? What are the building blocks? And the second thing is, how do I combine these AI models with tools and plugins? Right? So that's where these LLM app frameworks like LangChain, Llama Index, DeepSet, Semantic Kernel come into picture. So we have, as I said, native integrations with them, which allows you to use MongoDB Vector Search pretty effortlessly. So I'll talk about our integration with LangChain, right? So what this kind of a framework can allow you to do. So in your application building journey, you need a document loader, you need a vector store, you need something like a conversation history, and you need a semantic cache. So these capabilities with LangChain, we have a dedicated MongoDB LangChain package available in Python and JavaScript that provides you the best of class retrieval, and it is one of the most complete offering that's out there, which brings together the power of MongoDB's operational store with the vector store capabilities, right? So these are all capabilities. It's difficult to put together with bolt-on vector databases. We have a bunch of these advanced templates. So MongoDB parent document retrieval is one such example, which comes with a fast API compatible API. You can take this template and get started with an API that's spun off your MongoDB connection. And followed by, like, we recently launched a capability called semantic caching, super powerful capability to bring down the cost of some of these generative models. So it's different from a traditional cache. Semantic cache relies on vector embeddings to look at users' intent rather than the keyword of their search. It is powered by vector search and helps you put down the time and cost that your applications can perform with. So, and it's a similar point, right? As you extend, the retrieval systems are not enough. Now you want to bring together some tools, like based on a certain user's understanding of the query, you want to execute something in your Slack, let's say. Send a message, make an update. So that's where you can combine your models with your retrieval system and your tools. This is an example from Microsoft Semantic Kernel that talks a lot about building these co-pilot-like experiences that we have a bunch of integrations around. So that brings us to LLM observability and evaluation. So this piece is where you want to think about big questions of how do I really evaluate, right? Where LLM response is hallucinatory. As we are all aware, with this recent iteration, we are in a non-deterministic world. In the previous world of application development, it was something deterministic. There are unit tests, there are integration tests. Applications, your APIs always work as defined. But with LLMs in the picture, it gets into that randomness as almost a feature, which throws in requirement for your evaluation, right? Being able to be confident that it is working as expected. Bunch of techniques there we'll talk about too. And essentially, you want to be able to measure the performance of your system across the different stack, across the different layers that we talked about, so that you can iteratively improve things. On that front, like one piece is how do I evaluate if LLM response is hallucinatory? So one of the biggest emerging pattern here is using LLMs as a judge. So we use an LLM to put together a response, make a call to another LLM that's specifically fine-tuned for this purpose to be able to evaluate the response from the first LLM. And that's how you're able to get confidence on what's working, what's not working. So Petronas AI is one such company we have integrations with, where you can use these specifically trained models to understand how your application is performing. The second piece is the RAG, right? Like, so RAG we talked about, a lot of your practitioners, but there is an emerging RAG triad, like bunch of metrics that really make sense for evaluating your RAG system. So RAG broadly is 3-layered system, and we have identified these 3 metrics that are really relevant for understanding how your RAG is building. So we have a bunch of notebooks, example solutions with this company called Truera that goes into this depth. But now with RAG, you want to think about firstly your context relevance. Once you've retrieved from a vector database, like if that actually is relevant to the query, followed by the context, is this grounded? So that's a groundedness measure. And that's followed by the answer. So that way you're able to complete the scope that answer is actually relevant to the user's query. And it is backed by the right knowledge source retrieved from the database, putting together the RAG triad. So with that, build high-quality Gen apps faster with MongoDB Generative AI stack. We are excited, and we'll see what you can build. And with that, thank you so much. And if this session has been helpful, we'll really appreciate if you can pull out your phone, put in your reviews. We'll really appreciate any feedback on how we can serve you better. Thank you.